going to tell us Piezoaxionic Effect, and then right after we'll have some free caffeine and cookies, which I hope we'll do each week moving forward this semester, so as an incentive, both for us to come in time and for Ken to finish on time.
We'll try. Thanks, Josh. So today I'll talk about work that I've been doing with Mina Arvanitaki at Perimeter and Amalia Madden, who's a graduate student also at Perimeter. That was published, or that was put on the archive on that reference. So it's called the Piezoaxionic Effect. So piezo comes from Greek and it means to press or to squeeze. And so our main idea is that the QCD axion can generate a mechanical stress in a material and can literally press a material. In this paper, we propose a new, so we discovered this effect on paper and we designed, or at least put out the experimental concept for a potential detector. Yeah, so that's sort of towards the middle of the talk, but before I do that, I'm just going to review the motivation for the QCD axion, which is a weird puzzle, theoretical puzzle in the standard model. It's called the strong CP problem. Then I'll talk about the potential solution, which is the QCD axion, and what effects that the QCD axion has, in particular, the parity and time reversal violating interactions. And then I'll talk about the piezoelectric effect, which happens without the QCD axion even, and then our newly discovered effect. And I'll describe what the setup looks like. And if I have some time, there's a follow-up paper that we're doing with Amalia and Mina, as well as Andrew Garachi. But maybe I will have time for it. Okay. And feel free to stop me for questions at any time. So, the strong CP problem. So it's actually more appropriate to call it the strong P and T problem instead of the strong CP problem. So I know I'm not supposed to write down a Lagrangian, but let me do it anyway. Okay, so it was noticed in 1976 that in quantum chromodynamics, this term here is allowed. So it's this is called the theta term with some constant parameter theta naught times the strong fine structure constant divided by 8 pi, and then times the gluon field strength. Okay, and so if you don't know what this is, you can think of this as some effective chromoelectric field dotted into a chromomagnetic field. And then because there's 8 gluons, so you label them, there's 8 such fields. Okay, so that's, kind of what you can think of it like. So there's now energy density associated with there being a dot product of a chromoelectric and a chromomagnetic field. Okay, and this you can write as a total derivative. So perturbation theory has no consequences, but non-perturbatively it does have physical consequences. And in particular, so if you have quarks here, so if you add some quarks, which QCD has, then you can show that there's one physical parameter, which is called Theta Bar, which is the sum of this bare theta naught parameter and the phase of the quark mass matrix determinant. So basically, I can eliminate this phase by doing a field redefinition. I can just redefine what I call a quark to eliminate it and to sort of rotate this phase into the quark mass matrix. and vice versa. I can get rid of all of the phases in the quark mass matrix at low energies and rotate it into here. But this combination here is physical. Theta bar. And so notice, let me now talk about the symmetry action. So under parity, I send x to minus x, right? So under parity, the electric field flips. So the electric field is odd under parity, but the magnetic field is even. So if I do a parity transformation, the B field doesn't flip. Under time reversal, so if I send time to minus time, an electric field doesn't flip, right? If I have some positive charge here and a negative charge there, the electric field points from positive to negative, and if I flip time, that remains the same, so the electric field is even, but the magnetic field is odd. So I can get a magnetic field from an electron going around a loop like, or let's say a proton going around a loop like this, so I get a magnetic field that points up. But if I flip time, the direction of the proton reverses and the magnetic field also flips. So this term is odd under parity and time reversal. So that means that this parameter here breaks both parity symmetry and time reversal symmetry. And right, and so the problem is that we haven't observed parity and time reversal symmetry. So for example, I'll show you in a minute, but the puzzle is that, so this theta parameter is an angle between minus pi and plus pi, and the puzzle is that this angle has to be is experimentally determined to be less than 0.7 times 10 to the minus 10. I'll tell you from what experiment that comes from in a second. Okay, so one of the physical consequences is that you can calculate the vacuum energy density contribution proportional to theta. So you can write down the energy density of the universe as a function of theta, at least its variation. So theta bar goes from minus pi to pi, let's say, and you can calculate it in chiral perturbation theory, and you find that it has this periodic potential. It's not quite a cosine, but it's you can calculate this whole potential to about percent level precision. So for example, you can calculate the curvature here at the bottom. The curvature here at the bottom is you can calculate as m up times m down, so the up quark mass times the down quark mass divided by the square of the sum of the masses, and then times the pion mass times the pion decay mass. So that's the curvature at the bottom of the potential, with some corrections, but they've been calculated, and so this number is now known to about 1% or so. And even the fourth derivative as well, so that the whole global potential. And notice, for example, that if, let's say, the up quark mass, if you had one massless quark, this theta parameter becomes completely unphysical, because if I have a massless quark in the theory, then I can always rotate this theta into the quark mass matrix, but the phase of 0 is ill-defined, so that would also be a solution. So that would also be a solution and explain this low experimental value. However, we know that the up quark mass is not 0, therefore this is a puddle. So we live, exceedingly close to here. Is that clear so far? Okay, so what was then noticed by Roberto Pache and Helen Quinn in 1977 is that you can add a symmetry to your Lagrangian. So if you add, let's say, if you postulate the existence of some other quark, q bar prime q, and so now the theory can have a new symmetry, which is that you do a phase rotation of this complex scalar field capital Phi by eta I alpha, eta I plus alpha. You rotate this one by eta minus 2 I2 alpha, and this one is the same as complex scalar field. And so basically, by postulating the symmetry, you can rotate. Now this theta bar parameter is physically it's indistinguishable from this symmetry of your okay. So, but yeah, if this were the case, then there would still be some consequences. So Weinberg and Wilczek noted that this phase of this complex scalar field corresponds to a particle, which is now we call the axion. And so, so for example, this complex scalar field you would write as some vacuum expectation value Fa plus the sort of the radial mode, so the absolute value of capital Phi over root 2 times eta Ia over Fa. So this field here we would call the axion. Okay. And so if you do this, then you add to your Lagrange to this theta parameter basically this new phase, because this is part of the phase of the total quark mass determinant, which includes both the light quarks and this now heavy set of quarks. So now you make this you make the effective theta parameter dynamical. So this A field is now something that can vary as a function of time and space. Okay, so that was realized by Weinberg and Wilczek in 1978. So basically, now theta is dynamical. So here I've plotted the potential for this theta bar parameter. And so because it's now dynamical, this axion field here, so this A over Fa, can roll down to the bottom of the potential. And so this is kind of like a dynamical explanation for why theta is so small. So dynamically, this field would roll to the bottom, damp out, and settle here at the origin. So this is the QCD axion explanation for the strong CP problem, where it's absence of parity and time reversal violation in the strong interactions. And I should note that this solution of adding this heavy scalar field with heavy quarks, this was this type of construction was done by Kim, Schiffman, Weinstein, and Zakharov. And so Weinstein was with us last week. I think it's the same Weinstein, right? Yes. In 1970. Okay, so that's cool. So it solves one puzzle. The other puzzle that it solves is that there's energy density stored in these oscillations, and so if the initial conditions are such that you didn't start at the minimum in the first place in the early universe, the energy density associated with these oscillations can make up the dark matter of the universe. And in particular, if you want, let me write the typical RMS value. Let me just call this whole thing now Theta bar axion, and now it can depend on space-time coordinates. So the RMS value of this oscillation is, if you make it all of the dark matter today locally, you can compute it as follows. So it's equal to this. Okay, but we know what the mass times the decay constant is. So this, the mass of the field is determined by the curvature of this potential. So you can actually, because this piece here is known, you can show that this is equal to the mass times the decay constant as well. So we know this product of mass and decay constant. So therefore we know this denominator, and we find that the effective theta, if it's all of dark matter, would oscillate with an amplitude of a few times 10 to the minus 19. So it still solves it. So it's still small enough that we're not in violation of constraints, but there would be some oscillatory component.
Square, right?
Where?
MA squared, FA squared.
Yeah, MA squared. And yeah, so if this relation here would imply that the mass of this axion field is 5.7 times 10 to the minus 10 EV if this axion decay constant is close to the scale of grand unification. So a few orders of magnitude below the Planck scale. And it has this inverse relation, right? So the higher this decay constant, the lighter the axion, and also the more weakly coupled it is. So if I plot here the parameter space, goes to -1. So roughly the axion lives in this parameter space. Let's see if I can draw a straight line. Lives on this line, not quite straight, but so that's the axion sort of coupling or axion decay constant versus
What's the exponent at the top in your scheme?
10 to the 7
19 below.
and 19 below. So 10 to the 19 GeV, so Planck scale decay constant to 10 to the 7 GeV. So yeah, we know actually, I won't talk about it too much, but we know that the decay constant is excluded above 10 to the 8 GeV. So this is all excluded by not having seen excess cooling from supernova 1987A. Okay, so and we have some theoretical bias saying that the decay constant should be less than a Planck. And in addition, this is something Sergey has pioneered from black hole superradiance constraints. We know that the QCD axion is not in, so that there's some constraints here that look like this, where there would be an instability around black holes. So we also know that the QCD axion doesn't live sort of with Planck scale axion.
Yeah, one point which might not be very relevant at the night, so can FA be larger than F1?
It could be, but you need to do some additional model building.
Yeah, so for QCD
Yeah, but you need it's difficult, right? Because it can't be a simple model like this, because that would imply some super Planckian dynamics over which you have no control. So it would have to be, I think there are models like that, but it's difficult and it's not quite minimal. So we have some theoretical bias to be, not over here. So we live somewhere on this line, and the limit here, I think, is 50 milli eV. So it's somewhere between 10 to the minus 11 eV and 5 times 10 to the minus 2 eV.
There was this work building on fuzzy axion by Ostraker, Tremaine, and Witten, arguing for much lighter, and I thought they were invoking Planck.
So they say so they're talking about 10 to the minus 22 eV.
Right, and I thought, but what I was thinking they were saying it was for FA of order of
So
Planck mass.
so what they say is that what they say is, let's say that the effective field range of the scalar field is Planck scale, okay? And then they ask, how large is the curvature, should the curvature in this potential be? Not the QCD axion, but some different axion. How large should the curvature in this potential be for it to make up all of the dark matter? And so, and then you can find what the mass is. It's about 10 to the minus 22 eV. And then they say, oh, the typical mass squared times decay constant if F is m Planck. Let's say it's m Planck to the fourth times e to the minus s. And this s they estimate as m Planck squared over f squared. And so if you put f at the gut scale, then this exponential is large enough that this is some exceedingly small number. That's kind of the argument. But it's unrelated to the QCD
Oh, okay.
axion.
Somehow I didn't know.
Yeah, it's not the QCD axion we may talk about. All right, good. So I said there's this P and T violating parameter. The axion can explain why this parameter is small, and it could still oscillate a little bit around 0 and make up the dark matter. So what I'll tell you next is what the physical consequences are. So so P and T violating interaction. So one thing it can do is generate a neutron EDM. So if this is, let's say, a neutron, this would be a proton and a neutron. This is a pi minus. So and this is a photon. So this basically in the presence of this non-zero theta bar, the pion can have its regular coupling, which is large, let's say 13 or so. We can also have this P and T violating coupling, and this turns out to be 10 to the minus 2 times theta bar. Okay, and so from this diagram, a neutron can acquire now an electric dipole moment, and this electric dipole moment you can calculate to be about 2.4 times 10 to the minus 16 e times centimeters times theta bar. But it's been measured, and what was found was that well, they found 0, actually 0.00, if I remember correctly. No, just 10. Plus or minus 1.1, statistical error, 0.2 systematic error, times 10 to the minus 26 e centimeters. Okay, so they found 0, even though the naive expectation is 10 to the minus 16 times theta.
Out of curiosity, how
Yeah.
precise will you know? Do they think they know the 2.4 comes from lattice?
Not very well at all, within a factor of 3. So this is sort of the lowest high quality estimate I've taken. So this is conservative. So other groups, I think, using some QCD sum rules, the highest one is 4 times 10 minus 15. So it's maybe a factor. That's the highest estimate. So it's within an order of magnitude. Yeah. So sometimes you'll see that theta bar has to be less than.
And some rules not from lattice. Or it's not.
I think this is the best. This is the best lattice.
Oh, okay.
Okay. So and this is super small, right? So to give you some estimates, so let's say the neutron.
So how do they do it on lattice? Because
I don't know.
it's hard to do lattice with theta, right?
I think they extrapolate. Yeah, I don't exactly know. Yeah, I think they calculate it at unphysical quark masses and then extrapolate to the observed quark masses. It's difficult. Yeah. So to just give you some estimates, so a neutron is 2 up quarks and a down quark, right? So these ones are plus a third, and this one is minus 2/3 charge. The radius of a neutron is 10 minus 14 centimeters or so. So yeah, so you kind of get that the electric, like if a neutron was literally something like this, where the positive charges were sort of up and the negative charge was down, you would get an electric dipole moment. And if it was like this, well, then it would, the typical size would be E times 10 to the minus 14. So 10 minus 14 centimeters. Right, that would be the picture that I drew there. And so theta bar sort of parameterizes the amount of this electric dipole moment, but there's a small number involved, and I think it's related to the up quark mass divided by the pi on the k constant. Okay, so why does it? Let's see why a neutron EDM violates P and T. So let's say this is a neutron, and its spin, or let's say any general nucleon. So with a magnetic moment and spin that points up, and let's say it also has a dipole moment. It must point along the spin axis because there's only 2 degrees of freedom for a spin 1/2 particle, spin up and spin down. So let's say it points along the magnetic moment. If now you do a parity transformation, so if I do a parity transformation, then this electric dipole moment would flip, right? If I do a parity transformation on this, I send x to minus x, y to minus y, etc. So I would flip the dipole moment, but the spin would not flip. Right? So the spin would, or the magnetic moment would still point in this direction. So you can actually just by looking at one particle, you can determine whether you live in this universe or in that parity flipped universe. So by just observing a single neutron, you can determine whether parity is broken or not. And similarly, if you do time reversal transformation, then the spin is odd, but the dipole moment is even, so it still point this way. And then if you do a combined P and T transformation, you flip both. And you cannot distinguish a combined flip of P and T with our universe, because that would just be like a neutron with spin down, for example. And indeed, so by the CPT theorem, this theta parameter doesn't violate charge conjugation. So it preserves combined P and T symmetry, but it violates T and P symmetry separately. Questions? Okay. So yeah, the way it's actually this thing is actually measured. So the Hamiltonian is minus this let's say a nuclear electric dipole moment times the unit vector pointing along the nuclear spin dotted into the E field, and then likewise the magnetic moment dotted in, and then taking the nuclear spin dotted into a B field. So you know that just from this standard Hamiltonian, you get spin precession around the B field. That's also how the muon's magnetic moment is measured. So now if you have an electric dipole moment, you get precession around an E field. So by not observing that for a neutron, they were able to set this constraint. And so what I would like to do is measure this effects of theta bar in mechanical macroscopic systems, and for that the electric dipole moment is not the right quantity, and it's because of a powerful theorem by Schiff. I'm not going to prove it now, but Schiff's theorem says roughly the following. It says that if you have a macroscopic system of charged, so a non-relativistic system where all particles are charged and point-like, which is a good approximation for most macroscopic systems, right? Nuclei are non-relativistic, they are charged, and they're approximately point-like, and so are the electrons in most atoms. And so if that's the case, so then if you put, if you have a nuclear electric dipole moment, you can ask the question, what's the dipole moment of my full system of the atom? And it Schiff's theorem tells you that it's 0, despite the fact that there's some non-zero electric dipole moment of the nucleus, let's say. And the way to understand it is that basically the electron cloud will back react and shift a little bit to the right, so to cancel out exactly in this, if these three assumptions are true, the electric dipole moment from here. I think.
So what's the case where it just wouldn't, work? Like if you say one of those three are violated, like you can give an example.
Yeah, good. So for example, the non-relativistic approximation does not apply to electrons in large atoms. So for example, there's the electron EDM is measured in thorium oxide molecules, and thorium has a very large Z. So some valence electrons have an effect, are close to the speed of light, not quite, but have order 1 effective speeds. So this assumption is violated in large atoms, which is why the electron EDM is measured in those. And the thing that I'll use is that nuclei are not point-like. Okay, so I'll use a finite size of the nucleus. And so the second assumption is violated for a neutron, right? A neutron is not charged, so that's why you're able to do this. But for macroscopic systems, we don't have neutral particles floating around with EDMs. So Schiff's theorem applies. Okay, that's all I wanted to say here. And so, yeah, so you can calculate, so the neutron EDM is the lowest P and T violating moment of a nucleus, but there's other moments. So for example, in the list of moments is the nuclear electric dipole moment. There's also a nuclear magnetic quadrupole moment. There's a nuclear electric octupole moment. The one I'll be using today and in the work is a nuclear shift moment. So the electric dipole moment of a nucleus you can write as, let's say, the integral over the nucleus of the radius times the charge density. Okay, so that's the electric dipole moment. The shift moment you can write as, it's basically the radius squared weighted electric dipole moment. So let me write it. So you can write it as some EDM contribution that I'll tell you in a second, plus basically 1/10 times the sum over all charged particles in the nucleus, which are the protons, times the radius squared times the radius. Okay, so it's kind of like the very same formula times E. It's this very same formula. I'm just weighting the positions by radius squared, which is why it's a finite size effect. And so if you compute what this is in the end, so it has to point along the nuclear spin, and from here you roughly get that it's the nuclear size times the dipole moment, electric dipole moment of the valence nucleon. So what you should think about, what you can think of this like is that you have some core neutrons. Let's say you have helium-3, right? Then the core would be a proton and a neutron, and then encircling it would be a valence nucleon, which would be another proton. And if this proton has an electric dipole moment, then it acquires a shift moment of this size. And that shift moment, for example, is not screened by the electron cloud. Okay. Right, and so this first part, if you plug that in for,
Can you explain why, I mean, somehow one would guess that the shifts, I didn't know about the shifts.
yeah,
That it was some, you could like try to prove it by some minimizing energy, in which case you would have thought it would screen everything it could, and it could after all, why not? Why wouldn't it just shift a little more?
yeah, it's a
And
beautiful,
fix this.
it's a beautiful proof. It's 4 lines, but it really, yeah, it requires that it holds when the center of charge is the same location as the values of the bare electric dipole moments. But yeah, it doesn't apply. Like you can try it for a finite size.
No, I trust you, but I
Yeah.
just intuitively, I was searching, it's like it would, is there some fallacy in
So-
thinking that it's an energetic?
So maybe I'll give you a better heuristic explanation, right? So this is the Hamiltonian for for interaction of an electric dipole moment with an electric field, right? So let's imagine that this was not zero. So then I would, let's say, apply an electric field in this direction and look for a spin precession around that electric field. But this rearrangement you can understand as the fact that the nucleus wants to sit. It's a charged particle. It always wants to sit at 0 electric field, because if it was not, it would move towards the direction where the electric field is 0. So the nucleus never sees an electric field at its center if you imagine it's point-like. But then that's where you can violate it, because the electric field will be, the center of charge will now be here, but the EDM is located there. So if the center of charge is not exactly at the center of the dipole moment density, then you get a non-zero effect. So that's why it's not perfectly screened with finite size effects. That's kind of the classical way. But this shift theorem is an operator level proof in non-relativistic quantum mechanics.
Sorry, so do you mean the violation of the shift theorem is always induced by the valence photon, or?
Yeah, that's what I'll talk about. Yeah, so that's in the it's not perfect. In the nuclear shell model, you can think of all of the dynamics being generated by bound states of the valence nucleon. Just like in a hydrogen atom, all the energy levels are the valence electron, and these guys are sort of act as a source of a potential. That's just not an electric potential; it's some combined nuclear plus electromagnetic potential.
But is it important here that there is additional force on top of electromagnetism?
Yeah. So
Yes,
it's
that's
the bound states.
yeah.
That's what I'll talk about now. Yeah. Here, no. I mean, the valence nucleon is just, yeah. So you just compute the wave function, which is pure nuclear wave function, and then on top of it, you have some electromagnetic moment. And this is a subdominant contribution. So this turns out to be, if you compute it for the best types of nuclei, this is 10 to the minus 3 times theta bar e times femtometer cubed. Okay, but I'll talk about this now, which gives you a bigger contribution. So this contribution, so this contribution looks like, let's say if I have now, if I ignore the bare EDMs and I have some, again, nucleus with some core, and I only look at one valence nucleon, so I can have an asymmetric charge distribution. So I can have, if I have non-zero theta, I will get, in general, some pear shape where there's, say, more positive charge on the top side than down here. So this will give me, this will give me some effective shift moment as well. And that comes from interactions of the following form. So that comes from interactions like these ones. So if I have some nucleon line, the main potential between nucleons in a nucleus is through pion exchange, so by zero exchange. So that's the typical interaction that determines the bound states here. I mean, there's other meson exchanges, but the leading order at long distances, that's the main one. Now, if there's non-zero theta, it will get this G0 coupling, the same one in this diagram here. That's 10 to the minus 2 times theta. And so it will generate P and T violating interactions between nucleons. So this will generate a potential that's P and T violating, and it's the standard pion coupling times this parity violating coupling. So 4 pi r squared, and pion mass has a range of order. The pions come from wavelength, and it's parity violating because it's spin of nucleon 2 dotted into the separation direction. So this thing is P and T odd. So that's this interaction where this is a core nucleon and that's a valence nucleon causes this pear shape. Okay, so if the spin points that way, the valence proton, let's say, wants to be more in the direction towards the spin than not towards the spin. And this will give you, for the biggest nuclei, this will give you 0.2 e times centimeter cubed times theta bar, or something like that. So for the largest nuclei. And finally, there's another very cool effect that we'll use, and that's the fact that many nuclei have a core that's not spherical, as I drew it here. So in fact, many nuclei are football shaped, they're quadrupole-deformed, but some are just in the ground state, have octupole deformation, or have a pear shape. So a pear shape would violate parity, so they exist, the wave function of the whole nucleus is a superposition, 1 over root 2 times a shift moment pointing up, plus 1 over root 2 times just the whole thing flipped. So a pear shaped the other way. So if there's no axion, these nuclei don't violate parity because they're equal admixtures of shift moment up and shift moment down. But in the presence of an axion, you can mix these if theta is not 0. And so you can make, let's say, this one slightly more likely than that one by interaction of this nuclear core with a valence nucleon going around it. Okay, so the same interaction can sort of want to make this shape more likely than the other.
And this depends on the phases of this superposition.
No. So the same phase, that, let's say this is e to the I alpha, the same phase that appears here appears the other way in how the axion mixes them. So it's phase independent. And so for the biggest nuclei, this can be so for the biggest nuclei, for octupole deformed nuclei, it can be e times centimeter cubed times theta bar. Okay, so those are the ones we'll use. And so one examples of these types of nuclei are uranium-235, for example. So uranium-235 really looks like very much like this shape. I'm not even exaggerating it. Like the shape really looks like it, completely deformed with a very large quadrupole moment, very large octupole moment, on the order of 10-20%. Okay, so that's a lot of words. So what's the physical observable now? The thing that's, yeah.
Oh, my mind is blown.
Yeah.
Oh, I see, but this is along the direction of its own spin, so that's.
Yeah. So now what I'm saying is that there's now you know, this is parity. Let's do the symmetries. This is parity odd, but time reversal even, right? The spin is parity even, but time reversal odd. So just like an electric dipole moment, an alignment of the shift moment with the nuclear spin violates P and T.
But then, why it should be along the spin? Because it's complicated object, right? So why there is a
But
single-
if it's a spin 1/2 nucleus, for example, it only has spin up and spin down.
But here I'm talking about. So
Yeah, I mean, this is here I'm approximating it as sort of a rigid body with no deformations, which is not true.
Right.
So this is not, like, this would imply, yeah, so what are some indications of these nuclei? If it was really sort of a rigid body that has this shape and that shape, this would imply some parity doublet in the nuclear energy spectrum. Yeah, opposite parity levels. And so it's not exactly, you don't find exact parity doublets for these nuclei, but there's at least some indication that there's closely spaced opposite parity states within the nuclear energy density spectrum. So in reality, it's not a rigid shape like this. But it's very much like a molecule, like a carbon monoxide that can, you know, or ammonia that has parity doublets in the ground level state. Similar for nuclear state.
The argument that it has to be aligned with the spin is the same argument, maybe that wasn't what you're
It's here.
saying, as it is for the nucleon, that there's no other direction.
But even there, actually, I wasn't sure because, well, because it's not an elementary particle, right? It's an extended object, so.
No, but to the extent that it's a
But the
spin
excitations
eigenstate,
are much higher energy, right?
Right. So yeah.
Yeah.
So, yeah.
but still, if it's angular momentum eigenstate, it's neutral.
Okay, so, and you can calculate, so how does it interact now, this shift moment? So the shift moment, I should have written it down. The shift moment interacts with other charges, like so. So it basically, it couples to the gradient of the charge density, which would be, let's say, the electron density, like this, at the location of the nucleus. Okay, so it's a higher dimension, it's a high dimension multiple, so it's a finite size effect, so it's a short range electromagnetic interaction, and it couples to the gradient of the electron density. So if you have, let's imagine you have this pear shape in a nucleus, in an atom, so now I'm drawing the electron cloud around it, so it couples at the electron density at the location of the nucleus. So if my electron cloud has some S-wave admixture, as well as some p orbital, right, where this is minus and this is plus. The superposition of this S and p level will give me the gradient of the electron density at the nucleus. And it turns out, it's computed by the Russians, Zeldovich, Kriplovich. You only need to know the energy levels of this S and P levels, and then you can compute precisely this quantity with very good accuracy. And the reason for that is that very close to the nucleus, it's much like a hydrogen atom, right? So the effects of all of the other electrons in the atom don't matter. And so the expectation value of this operator, so this is all of the physics that I wanted to say, is 10 to the minus 23 electron volts if the axion oscillates with this amplitude of 10 to the minus 19. So for the biggest nuclei. And it's proportional to the spin dotted with the unit vector pointing along the gradient of the electron density. Okay, I did not manage my time very well. Good, so I'll skip some things. So I've told you all of the physics. The thing that we actually did, this was all known before, although not very well understood invented by many particle physicists. The thing that we realized was that this Hamiltonian can, this Hamiltonian here can back react on the lattice. So it can cause mechanical stresses in materials. And so a very similar effect is the piezoelectric effect. So let's imagine I have some lattice, one-dimensional lattice here. So if I compress this, then nothing much happens. I don't get an electric field. But if I now say, okay, these springs are stiffer than, so the plus to minus springs are stiffer than the minus to plus springs. So let's say that the straight lines are sort of, they buckle very well. If I compress it, I will get a system now that looks like this, minus, plus, plus. So these under compression, the system changes like this.
Does that mean compression? It's confusing. The straight lines were the stiff ones.
No. The straight lines are the sort of not so stiff ones, the very loose ones. So if I compress it, okay, I get from something without a dipole moment electric displacement to something with suddenly a bunch of electric dipoles. So this would be a linear relation between stress and electric displacement, and it's called, this would be some piezoelectric tensor. So you have a linear relation, but the stress is linearly proportional to the electric displacement. There's also some stiffness component proportional to the strain. And what we realized, and so this is very weird, right? So this is parity even, and electric displacement is parity odd. And so a linear relation between those two effects is only possible if your material itself is parity odd. And so that is true for quartz, it's true for DNA structures, right? DNA helix is left-handed, not right-handed. So macroscopic structures easily break parity. I'm right-handed, not left-handed, right? So I break parity. What we realized was that there's now an additional effect. Because you have parity violating materials, you should add a new term here that is proportional to a theta field in a parity violating material with polarized nuclear spins. And yeah, so that's basically the experiment. This oscillating Axion field that's oscillating with 10 to the minus 19 will cause a stress in a material and excite a bulk acoustic mode. I have a little demo to show you the piezoelectric effect. Okay. Prototype 0 of our experiment.
Sorry, this is 10 to the minus 19 what?
Dimensionless.
So,
but this tensor, this C tensor is defined as
sorry, that's the amplitude. No, I was thinking how you distinguish it from the other. It's probably the frequency.
Yeah. This would oscillate with the frequency given by the Axion. Yeah.
Which is not something that happens in nature and is masked by other effects.
No. So yeah, the experiment looks. The experiment is the following. So what we good. Our experiment is the following. So we take some piezoelectric crystal, so a parity violating material, and we polarize the nuclear spins inside here. And this would also give you a shift moment aligned with these spins. And in this material, if now you have an oscillating Axion background and you make sure you shield it from additional electric and mechanical perturbations, this Axion field causes a stress on this material, and it causes a bulk acoustic mode, mechanical mode in this crystal. And you know, if you have some, so that causes a strain in the material, but in this piezoelectric crystal, there's also E fields generated, as I'm about to show you. So there's similarly, if you have some oscillating strain, you will also generate electric fields and voltages. And so basically, the experimental setup looks like this. So now there would be some effective voltage due to the axion, and that couples to, in our system, an electrical readout. So you add a capacitor, an inductor, and eventually to, this is a simplified setup, eventually to a squid. So basically, the axion signal would generate a stress, which causes mechanical strain in this material. Mechanical strain causes an electric field through the piezoelectric effect. So you can think of it as some voltage in the circuit. And this voltage drives a current around the circuit. And a current will generate a flux that can be picked up by a very sensitive flux sensor like a squid. Okay, so that's the experiment. I have 1 minute left. This is, I was going to give it around to you. This is prototype 0. Okay. Okay, so I don't have a squid. This is a voltmeter. This is a tiny piezoelectric disc. So if I press on it, right? So if I introduce some stress, or if I press on it, I generate a strain, and the strain will give me an electric field between the opposing plates here, which I can then read out with the squid or a voltmeter. Okay, so if I press on here, I can generate, well, I shorted it, so I can generate 20 volts or so a second. So it's going on 0. So that's 13 volts. And so, yeah, this violates, you can try it out for yourself. Anyway, it violates Parity. So the bottom line is that if we,
Is this Axion?
it's not Axion. The bottom line is that we think we can build a sensor that covers the QCD axion range between 10 to the minus 8 electron volts, sorry, 10 to the minus 7 here, 10 to the minus 7 and 3 times 10 to the minus 11 electron volts. So this corresponds to tens of kilohertz frequencies to about 10 megahertz or so. I'm off by that. So yeah, that's the basis of the experiment. So, yeah.
Oh, sorry.
I'll take questions now.
Where is this range coming from? Is it the limit on the design, or does it come from the physics?
The physics, right? So basically, what it wants to do is, let's say I'm not pressing from the sides, but let's say I have some, let's say I add a shift moment for the positively charged nuclei only. So if theta is large and positive, it's energetically more favorable to compress because of this interaction. So that's what happens. So I have an oscillating shift moment, which gives me a stress that wants to compress or stretch this material, and it's only possible if I have in a parity violating material. So that's the experiment. So you take that thing, you polarize the nuclear spins, and it wants to vibrate proportional to an axion field, just like it would want to vibrate if you apply an electric field.
So this bound, that's assuming that axions made all of the dark matter? Or?
Yeah. So for this we require the axion to be all of the dark matter, and then we think we can look in this range.
Is this line like a bunch of different piezos, or is there some smart way to do some scanning of mechanical resonances, or what's the most straightforward way to cover this full mass range?
Yeah, so with one crystal you can cover 10% fractional bandwidth. So if you want to cover one E-fold, let's say between 3 and 6 times 10 to the minus 11 EV, you would need on the order of 10 to 20
With like varying thicknesses.
with varying thicknesses. Yeah, but so for example, that little disc that's going around, that costs $1. Okay. The actual experiment will have to use a fancier material with fancier nuclei, or heavier nuclei, so it will be more expensive. The material
It's like
costs.
hundreds of crystals across.
Yeah, so I think at this point, this would be, the size of the crystal would be, I think, this is 40 centimeters. Yeah, actually, a factor of 10 higher. This material here would be 40 by 40 by 4, so 4 centimeters thick and 40 centimeters wide. Just one would cover like a 10% fractional bandwidth. If you have 10, you would cover a full E-fold. Over here, as you go to smaller and smaller sizes, so this here would be, I think, 10 millimeters squared and 0.1 millimeter thick, kind of like the thing that I have going around. And this is too small that the thermal noise would basically swamp everything else, and you wouldn't achieve the sensitivity. So here you would need a few thousand, 10 to the 4 or so. But it's easy, you can just put them in series, many of these little disks. And the total mass of even just these 10,000 resonators with this thickness would just be a kilogram or so. And I calculated what the limit would be from just not pressing the thing. And you would set a limit, a low frequencies only, so around here, of about 10 to the 2 GeV. Okay, so you would set a broadband limit here. Yeah, and the FA at 1 Hertz frequencies would be 10 to 22 GeV. So you're about 20 orders of magnitude off with that setup. So you could improve by 9 orders of magnitude by using a squid, and by 6 orders of magnitude by going to millikelvin temperatures to polarize more of the nuclear spins, and by another few orders of magnitude by using a bigger crystal than just a tiny little $1 thing.
So what's the lower cutoff?
We just cut it off here because it becomes very expensive to build these large crystals. But it's true that there have been gravitational wave detectors based on mechanical resonators that were 2 meters long. So it's not that crazy to extend another order of magnitude, but it just becomes more expensive, and we don't know if you can grow piezoelectric crystals of that size. So it needs to be a single crystal, right? Not some metal hunk of material, which were the 2 meter detectors.
And so the frequency range is, used a lot for
Right.
electromagnetic
Yeah.
waves. So you need a very good screening, I imagine.
Yeah, so you need to put this in some superconducting shield, which shields regular electromagnetic waves, but not the Axion wave. I think similar screening levels are used for other electromagnetic resonators in this regime. In particular, so what I didn't show is ADMX is already ruled out about a little less than an E-fold at around between 10 to the minus 6 and 10 to the minus 5 EV. So they achieved the right levels of screening already. Going below 1 kilohertz is difficult to mitigate vibration noise, but yeah, both vibration noise and electromagnetic noise should be screenable at those frequencies.
Is this assuming like you've isolated it completely to some like thermal and vibrational level?
Yeah. So this is the noise level that sets the signal to noise ratio is a combination of thermal noise. So basically this system is lossy, so it has some connections with a thermal bath. So the main thermal noise is just the Brownian noise of this harmonic oscillator in here, plus the squid flux noise, which is how, that voltmeter can read 10 to the minus 4 volts. The squid can read out about 10 to the minus 12 volts, as referred to sort of the Axion voltage. So that's the squid flux noise, and then there's squid back action. And so the combination of these three noise sources limits the sensitivity here. And that's why the squid back action is why it sort of curves up here. So it's really difficult to extend it to higher frequencies because these ones, if you have a quantum limited squid, even if you have a squid at the standard quantum limit, you cannot really, I mean, your curve would just continue like that and get worse. So, but up to 10 to the minus 7 with a quantum limited possible.
And it scales by square root of explosion?
Yeah, this curve goes down like integration time to the minus a quarter power. So if you want to improve by a factor of 2, you have to wait 16 times longer.
Why the quarter?
Square root of the power.
Square root of power.
Any more questions? We're gonna continue talking over cookies and caffeine.
So did you say Andy Garachi is gonna do this?
What he's going, so I didn't talk about this, but the last thing is
Yeah.
normally